All right, today we're jumping into one of my absolute favorite algorithms in all of machine learning, the random forest. And we're going to figure out how a little bit of chaos actually leads to some seriously impressive results.
And this is really the core question, the big paradox we have to unravel. How on earth can making a model more random actually make it more accurate? I mean, it just sounds wrong, doesn't it? You'd think randomness would just create noise and mess things up. But for random forests, that randomness is their superpower. So let's dig in and see how this works.
Okay, so before we can understand the whole forest, we got to start with a single tree. The basic building block here is an algorithm called a decision tree. And a great way to think about it is like a single, super brilliant, but maybe a little bit unstable genius.
And here's the deal with our unstable genius. On one hand, a single decision tree has what we call low bias. That's a good thing. It means it's super flexible. It can learn all the really complicated nitty-gritty patterns in your data. But, and this is a huge but, that's also its biggest weakness. It suffers from high variance. It's so flexible that it's unstable. I mean, if you change just a few data points in your training set, the tree can look completely different. It basically memorizes the noise instead of learning the signal. You've heard of it before, it's classic overfitting.
So, what do you do if your one genius expert is brilliant but totally unreliable? Well, you don't just trust that one expert, right? You get more of them. You build a whole committee. And this is the first big idea behind building a random forest.
Now, this whole committee of experts idea has a fancy name, bootstrap aggregation, but pretty much everyone just calls it bagging. And the idea is actually super simple. Instead of putting all your eggs in one basket and training one big model on all your data, you train a whole bunch of models, each on a slightly different piece of the data. Then, you just let them vote to get the final answer. Simple as that.
Okay, so how does this bagging thing actually work in practice? It's pretty cool. First, you take your original dataset and you create a bunch of new, smaller datasets from it. Let's say you make 100 of them. The key here is that you sample with replacement. That just means when you pick a data point, you put it back, so you might pick it again. This results in each of your 100 datasets being slightly different. Then, you take each of those unique datasets and you train one of our unstable genius decision trees on it. Now you've got 100 different trees. So when a new piece of data comes along, you just ask all 100 trees, hey, what do you think? And you either average their answers or take a majority vote. Done.
And this is where the magic happens. Any one of those trees might be totally overfit and making some pretty weird predictions. But when you average all of them together, their individual mistakes, they just tend to cancel each other out. It's that classic wisdom of the crowd idea. The group's final decision is way more stable and way more reliable than any single expert's opinion. This is how we tackle that high variance problem we saw earlier. It just gets smoothed out.
All right, so we've got our committee, we're averaging their votes, we've reduced the variance. We're done, right? Problem solved? Well, not quite. There's a catch. A more subtle problem starts to creep in. What happens if our entire committee of experts all start to think and act the same?
Think about it. Let's say you're trying to predict house prices, and one of your features is square footage. That's a really strong predictor, right? So what's going to happen? Pretty much every single decision tree you build is going to jump on that square footage feature right at the very beginning. The result? All your trees start to look suspiciously similar to each other.
And there's a mathematical term for this similarity. It's called correlation. The best way to think about correlation in this context is as a measure of groupthink. If your trees are highly correlated, it's like they're all in an echo chamber. They've all learned from the same dominant features, and worse, they're all likely to make the exact same mistakes.
And that's the real problem, right? That's the echo chamber. If everyone in your committee is making the same mistake, then averaging their votes doesn't do you any good. You just get the average of a bunch of wrong answers. The wisdom of the crowd only works if the crowd has diverse opinions. So yeah, bagging helps, but this correlation problem is holding it back.
So this finally brings us to the random part of Random Forest. This is the stroke of genius that solves the groupthink problem. The inventors found an incredibly simple yet powerful way to force the trees to be different from each other.
So that's the big question we need to answer. How do we intentionally break up this groupthink? How can we force each of our expert trees to look at the problem from a slightly different perspective?
And the answer is surprisingly simple. Here's the secret ingredient, the one thing that turns a regular old bagging model into a powerhouse random forest. It's called random feature subsampling.
This is such a clever little tweak. Here's the rule. Every time one of our decision trees is about to make a choice, what we call a split, we don't let it look at all the possible features. No way. Instead, we only show it a small random handful of them.
By doing this, we force the trees to explore different features and find different ways to make predictions. That one dominant feature can't just take over everything anymore. This is how we break the correlation.
And this isn't just some clever trick that feels like it should work. The math behind it is solid. Let's take a quick look at the formula that really explains why this is so powerful. Okay, don't let the symbols scare you. The concept here is what's important. The total error, the variance, of our force is basically made of two parts. See that second part, the one at the B on the bottom? That part gets smaller and smaller as you add more trees. That's our wisdom of the crowd benefit. But now look at that first part. That's the groupthink term. It's got that row, the correlation, right in it. And notice it doesn't get smaller when you add more trees. It's a stubborn floor on your error. So the only way to make our model even better is to directly attack that correlation.
And check this out. Here's the proof in the pudding. Look at these results. A single tree has an error of about 0.06. Okay. Now we use bagging, we average a bunch of trees, and the error drops to 0.045. That's pretty good. But then we add our secret ingredient, the random feature selection, to make it a true random forest. And boom, the error plummets down to 0.027. We've cut the error from the bagging model by almost half. That's a huge improvement.
So let's just nail this down. That little bit of randomness we added isn't random for the sake of it. It has one specific job: to crush the correlation between the trees. It breaks up the groupthink. And by doing that, we unlock the full supercharged power of averaging, which gives us a much, much more accurate model.
Okay, and if all of that wasn't cool enough, there is one more amazing thing about this whole process. It comes with a free gift, a totally built-in way to check how well your model is doing without you having to do any extra work.
Okay, so remember how we made all those little data sets by sampling with replacement? Well, there's a neat mathematical quirk to that process. It turns out that, on average, for any one of those samples you create, about 37% of the original data gets left behind.
So think about what that means. For every single tree in our forest, there's a chunk of data, that 37%, that it was never trained on. It has never seen it before. We call this the out-of-bag sample. And what do you call data that a model hasn't seen before? A test set. We get a free built-in test set for every single tree.
So what we can do is use these out-of-bag samples to get a really good, unbiased estimate of our model's performance on new, real-world data. It's called the out-of-bag error, and the best part is it's basically calculated for free while the model is training. This saves you so much time and effort compared to other methods like cross-validation. It is an incredibly powerful and efficient feature.
So when you step back and think about it, what's the really big idea here? Random forests teach us something pretty profound that goes way beyond just coding. It's this idea that by intentionally injecting a little bit of randomness, you can force a diversity of perspectives. And when you bring together all those different viewpoints, the collective outcome is way stronger, way more accurate than what you'd get from a single genius or a committee full of clones who all think alike. And that just makes you wonder, doesn't it? Where else is that exact same principle true?